Today we are going to deal with circular motion. A particle is in uniform circular motion if it travels around a circular arc at a constant, that is uniform speed. Although the speed does not vary, the particle is accelerating because the velocity continuously changes the direction. Our explanation will roll around this diagram. I'm your instructor, Dr. Shyamkant Anwane, Professor and Head Department of Physics, Sri Shivaji Education Society, Amravati Science College, Nagpur. I shall be referring to the famous book written by Halliday, Resnick and Walker in the title Fundamentals of Physics. A particle is in uniform circular motion if it travels around the circular arc at a constant uniform speed. Although the speed does not vary, the particle is accelerating because the velocity changes in direction. You have seen in the figure the relationship that appears in the diagram between velocity and acceleration at various stages during uniform motion changes. Both vectors have constant magnitude, but their direction changes continuously. This is a very important thing to be highlighted. The velocity is always directed along the tangent to the circle in the direction of motion, while the acceleration is always directed radially inward towards the center of motion. Because of this, the acceleration associated with the uniform circular motion is called centripetal, meaning thereby center seeking acceleration. As we prove next, the magnitude of this acceleration is A equal to V square upon R. We are going to prove this. In addition, during this acceleration at a constant speed, the particle travels circumference of the circle, that is 2 pi r, in time capital T, that is called period. So we can write period T is equal to distance traveled 2 pi r divided by the uniform velocity, and 2 pi upon 2 pi r upon v is called period of revolution or simply period of motion. It is in general the time for the particle to go around a closed path exactly once. Now our objective is to unfold the centripetal acceleration appearing in the uniform circular motion. So here you can observe the circular track around which the particle is moving, and at any point P it has coordinates xp, that is xp distance along x-axis, yp distance parallel to y-axis, and this point P is at distance r from center of the motion, that is center of the circle. And if you draw a line from center to point P, which is of distance r, makes an angle theta with x-axis, usual circular geometry. So here the velocity at this point is along this direction, this pink direction, showing v bar. Incidentally, this v bar makes theta angle with this vertical extended line, and this velocity v bar can be resolved into x and y component, and vx is equal to minus v sine theta and vy is equal to v cos theta. Why vx is minus? You can imagine if we resolve this into two directions, this will be x direction. So it will be directed, I'll try to draw this. It will be along minus x direction, and the vertical component, if I extend, it will be plus Vy. So here you can observe Vx is equal to minus V sine theta and Vy is equal to V cos theta. if we replace Vx and Vy from this circular geometry equations, we obtained V bar. And now we want to replace this sine theta and cos theta from this triangle. Here theta, sine of theta will be front yp upon hypotenuse r, cos of theta will be adjacent, that is xp upon r. So if we replace sine theta and cos theta, we obtain this equation. Our aim is to obtain acceleration. So to find acceleration, we need to differentiate velocity once with respect to time, and we'll be able to obtain acceleration. Now moving forward, Vx is minus sine theta as I said, and Vy is plus V cos theta, and A we are writing as d dt of V, and V is uniform, R is fixed, so that is out of differentiation, and we are left with time differentiation of Yp times I cap, that is a unit vector along x direction, plus V upon R dxp by dt j cap. Now this is y component of velocity dy by dt at point P, and this is dx by dt at point P will be Vy and Vx respectively. Now my whole objective is to make out acceleration, and this is my diagram for acceleration. Let us try to understand what is happening here. Our last equation was a bar equal to minus V upon R Vy I cap plus V upon R Vx j cap, where Vx and Vy we already know. If we substitute that, we'll be able to obtain something very interesting, in the sense A is equal to minus V square upon R cos theta minus V square upon R sin theta. So both Ax and Ay component you can locate, they are in negative direction. So this is Ax component and this is Ay component, and if you draw the resultant A bar, which is this one, that makes an angle phi, say with x-axis. So Ax I am rewriting as minus V square upon R cos theta and Ay as minus V square upon R sin theta. We can find out magnitude of a vector, we very well know it from 11th level physics. So as we are on the new slide, I am rewriting my equations, and now magnitude A, which simply can be written as A, is equal to under root of ax square plus ay square. So you have to club the whole thing and square that, and if you take it out of the square root, it will be v square upon r cos square theta plus sin square theta. Obviously the square root will be unity, and the centripetal acceleration is simply v square upon r. So we have established this equation, and the angle phi that I have shown you in the last slide, that indicates tan of phi is equal to y component of acceleration upon x component of acceleration, offers us simply tan of theta. This means that we are left with nothing other than phi is equal to theta. So here I have combined all the diagrams together to show you everything, that is a point P having coordinates xp, yp, and it is at distance r from the center. It has velocity vector v bar that can be resolved into vx component, which is along minus x-axis, and vy component, which is along positive y-axis, and acceleration, which is directed towards the center, that also has two components, one along minus x direction, another along minus y direction, and here we have established theta is equal to phi, or phi is equal to theta, which means that it is directed along the radius r towards the center of the circle, as we wanted to prove. So thank you very much for your attention.